This is a hand lapping plate made in a special grey iron. The lapping fluid being used contains thousands of small particles of very hard material, such as silicium carbide or diamond. These are easily visible under the microscope. This is the principle of lapping, the rubbing together of two flat surfaces with lapping fluid between them. As the material is removed by the particles, it is flushed out with the lapping fluid as waste. The lapped surface of the part is a dull grey colour. Under the microscope, the surface presents a flat, even structure, similar to a sandblasted surface. Illuminating with monochromatic light reveals the roughness. The accuracy and smoothness of the part are improved by lapping. In machine lapping, even wear on the part is achieved by moving it to and fro across the rotating lapping plate. We are now going to watch a single plate lapping machine being set up for work. The lapping fluid, consisting of lapping powder and lapping oil, is poured into the supply tank. A new cast iron lapping plate must first be run in. For this process, 3 correction rings are used. The motor drives the lapping plate only. Friction causes the correction rings to turn with the plate. The rings spread the lapping fluid evenly across the whole surface. They lap the plate flat and keep it that way during lapping of the parts. Now the parts can be loaded onto the machine. A special form would be used to hold delicate parts. The necessary force is applied by means of a pressure plate. The surfaces of the plate and the parts are worn away evenly by the millions of hard, loose particles rolling between them. If the parts are suitably shaped, they can be placed to fill the correction rings. Unsuitably shaped parts, lapped without a form, may tend to tip, leading to edge damage. The parts rotate upon themselves and turn with the rings. Now we are going to follow the kinetics of lapping. The yellow marks on the plate and on the rings will help us to follow the movements. For each rotation of the plate, the ring also rotates once. To get even stock removal over all the surface, the cutting speed at all points on the lapping plate must be the same. We can explain this as follows. The outer diameter of this plate, and therefore its linear speed, is 5 times that of the inner diameter. At a point on the radius, the ring is moving in the same direction as the plate. At another point, the ring is moving in exactly the opposite direction. The difference between the linear speeds at the 2 points of contact between the ring and the plate, taken on the same radius line, is the effective or working cutting speed. If the cutting speed is the same everywhere, stock removal is regular. Stock removal is the same on all parts held inside the ring. The lapping fluid consists of a lapping oil containing hard particles. As the loose particles roll between the lapping plate and the parts, the material is ground away. As tiny amounts of material are broken away at millions of points, the surface becomes flatter. After lapping, the surface has a dark grey colour. Through a microscope, it appears as an even structure. This structure is typical of a lapped surface. By replacing the lapping plate with a sheet of transparent perspex, we can show the action of the particles in the lapping of an aluminium part. The microscope shows how the rolling particles cut into the surface and roll away on the right. This image from the electron microscope shows the cutting marks left by the particles. The rolling cutting marks are repeated again and again. The more particles in action, the more marks. In practice, the final structure is obtained by the action of millions of particles. Here, the structure is illuminated by monochromatic light and magnified 10,000 times. The roughness value is 0.3 microns. A toolroom check of flatness is the method of using an optical flat under monochromatic light. The optical flat, made of special glass, is laid on the surface. The interference band shows the degree of flatness. Deviations from flatness are revealed by curved bands. This part, for example, has been lapped to perfect flatness. These surfaces are not only flat, but also parallel. Each band space represents 1 micron. Now let's see how a single plate lapping machine can produce parallel surfaces. The faces of this hydraulic equipment flange must be flat and mutually parallel. The soft felt disc has a special function. When non-parallel parts or those of unequal thickness are being lapped, the elasticity of the felt equalizes the pressure. After lapping one side with the felt disc in place, the parts are turned over and lapped without the disc. The high spots take most of the pressure and are the first to show signs of stock removal. The pressure plate bears against the finish lapped surfaces, so the pressure is transmitted to the full surface, and the final operation produces a flat surface parallel to the initially lapped one. Sometimes the part sticks to the pressure plate. The lapped surface of this ring gauge has a roughness value of only 0.31 microns. It looks immaculate, but seen magnified 1,600 times, the hills and valleys are very pronounced. Some lapped surfaces have a roughness value of only 0.06 microns. Slip gauges, for example. Their surfaces are so flat that there is no space for air between them, and they stick together. The roughness value achieved can be controlled by varying the hardness of the lapping plate. Here are a few examples of lapping plates of different types. This lapping plate is made of copper. During lapping, the particles become bedded into the soft plate surface. Instead of rolling, the particles are dragged across the surface of the part. This is shown by examination under the microscope. The lapping particles leave fine markings in the material. In this case, lapping produces a polished surface. The surface of this vacuum pump vane must have a roughness value of only 0.05 microns. This is necessary to create a perfect metal-to-metal seal. The parts can be wrung together so that they stick, resisting a separating force of 270 newtons. A hard lapping plate can have annular recesses filled with copper. The surface structure then produced is one corresponding partly to the rolling action and partly to the cutting or tearing action of the particles embedded in the soft areas. This magnified surface has marks made by both rolling and cutting. The surface is dull polished after lapping. Here you can see the cutting marks. In the case of this part, its functioning capabilities were considerably improved by modifying the lapping process. Tall parts require special handling during lapping. Here the parts are held firmly by magnetic force. Lapping is even possible for cylindrical surfaces. These piston pins are lying in a cage, like the needles in a needle bearing. A second lapping plate lies on top and rotates in the opposite direction to the lower plate. The stock removal is caused by the offset position of the pins, which produces a force resisted by the lapping plate.